So similar to the last one, we generally have a car, although there is a plane I believe that I've assigned that has an airplane. I'll talk about briefly. Car going around a curve, and the net force has to be the centripetal force. Otherwise, it wouldn't move in uniform circular motion. But in this case, if we look at the car from back here, we're not going to rely on friction. Racetracks, for example, you may recognize if you watch a lot of NASCAR. If you do, by the way, ask yourself why. But racetracks are oftentimes banked as the car goes around the curve. We're going to say there's no friction whatsoever. It's going to eliminate that out of the situation. Not that you shouldn't be able to handle it, but we'll take it away for a second. Now, unlike other inclined plane problems, in this case, it's going to help us if we keep our axes, we don't tilt them, we just keep our axes like so. We end up with the weight of the object downward, mg, and the normal force this way. That's interesting. So that would be a free body diagram. What would a component diagram look like? Well, component diagram is going to have the weight down, the y component of the normal force canceling that, and there's going to be an x component of the normal force, and guess what? That is our centripetal force. So it's actually the normal force that does the job. So how can we find that? Well, that's going to be, let's see, we know that the trick is the angle, of course. It's an inclined plane, and so therefore the angle is a little funky. This angle that they give us here is not the reference angle. As a matter of fact, it's the, let's see, it is this angle, but we want this one in blue. That's what we want. So we're going to do 90 minus reference, or let's just do it this way, like we do with inclined planes. When they give us that angle of inclination, we are going, for the inclined plane, we are going to make the x relate to the sine now, and the y relate to the cosine. We're going to switch the two. That means a couple things. That the y component of the normal force, which is equal to mg, is going to be equal to the normal force times the cosine of that angle. So, for example, if you needed to find the size of the normal force, you could use this to find it first, and then go over to the x dimension, where the only game in town is the x component of the normal force, and therefore it is the net force, and therefore the centripetal force. And that would be normal sine that angle inclination would equal to mv squared over r. I would like to point out that once again, if n can come from over here, so n over here is going to be mg divided by cosine. We could bring that over and stick it in there. Let's see, we got mg sine theta over the cosine of theta equals mv squared over r, and sure enough, just like before, the masses cancel out. In fact, it turns out g times the tangent, sine over cosine is tangent, of that angle is actually your centripetal acceleration. So this is a helpful relationship. Now once again, your AP is not going to give you this, quote, formula for a banked curve. It's going to be that specific. It's going to expect you to work through it, what I just did on your own. But as a helpful way of looking at it right now to get through a problem if you're stuck, keep this in mind. That this tangent of your angle of elevation on the bank, the tangent of that angle, times g will give you centripetal acceleration. Of course, you may not know the angle or something. You may have to use velocity and radius to get it first.